Okay, greetings everyone. I want to, on the behalf of Nejc, I want to share our experience with PYNQ for accelerating FPGA application development. What is PYNQ? PYNQ is represents Jupyter-based framework for developing application targeted for the FPGAs. In order to do that, let's say the core elements of PYNQ are overlays as as hardware abstraction. These overlays contain bit stream that will be loaded on the FPGA fabric, while the application development is done purely in Python, an easy to use, easy to master language, which is run in the Jupyter notebook, which runs on web server, and the web server runs on the host processor. Okay, so how do we use PYNQ? Okay, the PYNQ is intended for software developers in order to use custom-made accelerators. Okay, so let's say that we had a group of hard-working hardware engineers, and they prepared a couple of overlays, couple of hardware designs. So what does our developer needs to do in order to start using these accelerators? In Python, he only needs to write these two lines in Python, and after he executes it, the CPU will read the overlays, which are usually stored on the SD card. Then the CPU will load it onto the FPGA fabric, and it can utilize the developer can utilize the accelerator. If he gets bored from the first accelerator, he can easily reprogram the fabric just by rewriting the name, loading the next overlay. So the overlays, as such, are some kind of similar to the software libraries that we use in our programs. So basically, the software libraries are developed by third parties, and we use them. We only use them for their functionality, and not interested how the functions are implemented in the library. Similar goes for the overlays. So when we talk about overlays, let's have an example of one overlay design. So here, this overlay design, integrates the accelerator for scalar addition, and it's connected with the Zinc core. Basically, it contains host processor. So when we implement this in Vivado, we get bitstream, and together with bitstream, the overlays contain design metadata, register map, as well as the operating frequency of our design. It's really useful to write a driver for your accelerator, and it's done in the Python. So basically, we start by defining class, in which inherits some default IP class. Then we pass the description, which contains the register map of the accelerator. And we bind this driver to the specific IP by providing the vendor, library, name of the IP, and the version, VLNV parameters. And at the end, the most important thing is to define the functionality which this driver will provide. And concerning after the driver is after we develop driver, we just need to reload the overlay, and we can use it. We can use this driver by simply deaccessing the object overlay and start it. So basically, this is done. This computation is not done on the whole CPU. It's done on the accelerator. Okay, this was the example. What we did in our case, we develop accelerator for MDP5 hash function. So a little bit background about MDP5. MDP5 is nothing more than an algorithm for hashing messages. It's one of the oldest algorithms and one of the simplest ones. So the hash algorithm takes the message, then divides it into chunks of 512 bits, and for one message it outputs 128-bit hash value. So we wanted to see how does FPGA fabric accelerate the computation, and more importantly for this presentation, how the PYNQ enables the usage of this accelerator. Okay, so hardware software co-design. So when we were developing, we were first in parallel designing the host application and the accelerator. On the host application, we used several messages and segmented them into 520-bit blocks. And we segmented and we mixed them in this kind of interleave fashion. So basically, this is the first block of first message, the first block of second message, and so on. Our accelerator can do 64 messages in parallel. Then we have the next group goes the second blocks of the messages. On the FPGA fabric, we developed an accelerator that receives input data, and it utilizes pipeline approach. The MDP5 algorithm has this 64 iterations, so we designed the accelerator 64 stage in the 64-stage pipeline fashion. Then, after we computed it, we return the results back to the host. Okay, this is the architecture of the whole. This is the architecture of the whole design. So basically, here is this Zinc system, which contains the host processor and memory. And here we have the MDP5 accelerator, really small on this figure, but it's the biggest element in our design. And we have this XC-DMA engine, which feeds our accelerator. Concerning the performance comparison, we compared the performance. Of calculating MDP5 on host processor and calculating on the using accelerator. And you can see this blue line represents the CPU performance, and this bars. Orange-green bars represents the performance from accelerator. We let's say achieved better performance from the FPGA accelerator. Still, it's not that big. But what is the bottleneck in our implementation? The bottleneck in our implementation isn't the accelerator itself. The accelerator, if you see this orange parts, and the bars represents the speed of the calculation of MDP5 algorithm, and these green represents the input data pre-processing, which is not done on the accelerator but on the host CPU. So host CPU is the employment of host CPU is the bottleneck in our design. When we talk about resource utilization, we can see that our MDP5 algorithm accelerator takes the most area in the design, but compared to the power consumption of the CPU, it delivers slightly lower power consumption. Okay, so in the end, we throughout the research we developed accelerator and the and the software application. If we had the accelerator already prepared, we needed only to write this in our host application, and we could do this in a sip of coffee. And with this slide, I will conclude my presentation, and I'm open to the questions. Thank you.
Thank you, Ratko. It's time for questions. So, any digital designer here want to ask? Yes, Andrei?
Okay, thank you for presentation. I wonder, is a PYNQ tied to a specific device family or board, or can it be exported to others?
Yeah, okay. Concerning the PYNQ, it stands for Python Productivity for Zinc devices. So it's primarily targeted for Zinc devices, but it can also target for Alveo devices, where this host processor is not the embedded one on the board, but the processor on the node or PC. But still, you cannot use PYNQ with every device, every FPGA device in Xilinx from Xilinx vendor.
Okay, thank you. Any other questions here? Okay, then I will ask you, so is this that kind of approach kind of really in academic level or already targeting also in the industry?
Yeah. Okay. So so this is probably really used. This is probably really useful for industry applications. But here we only cover this from academic standpoint.
Okay. So good news. Okay. Thank you for your answer. Then once again, one applause for him.